In this video, we're going to look at two examples of using implicit differentiation, looking at curves and finding some tangent lines and tangent slopes and all that fun stuff. So here's the graph of the equation y cubed plus y squared minus 5y minus x squared equals -4. So I made this on Desmos. Desmos.com is a really cool website. I think I've mentioned it at least once before. Your calculator, if you have a graphing calculator, it can't graph these kinds of things because if you notice, like the button is called y equals, that, when you put in the equation, the function, and we just can't do that with these. So if you want to see what the graphs of some of these things look like, you have to go to the internet to do so, which is totally fine. So we want to find the slopes of the tangent lines at 1, -3, at -2, 0, and at 1, 1. That's in part A, and then in part B, we want to find where the curve has a horizontal tangent line. So all of the things that we've already learned about derivatives still apply to implicit differentiation. We're just adding to the things that we can find the derivative of. So it looks like we want to find dy dx first in order to say anything about the slopes or horizontal tangent lines, right? That means tangent line means derivative, or at least it helps us find the slope of the tangent line. All right, so I think the first thing we probably want to do is go ahead and differentiate both sides of this equation with respect to x. That's step 1 in our guidelines for implicit differentiation. Oops, I don't know where that came from. -4 is on the right-hand side, so there we go. All right, we have to remember that we should multiply by dy dx every time that we differentiate a term with a y. So on the left-hand side, we'll take the derivative of y cubed. That'll be 3y squared times dy dx. Then we'll subtract the derivative of y squared. Also, I don't know where that minus came from in the actual equation. It should be a plus. Sorry about that. So we'll add the derivative of y squared. So that'll be 2y, and then times dy dx, right? Because again, we differentiate a term with y. Then we subtract the derivative of 5y. That's 5. Then we have to multiply this term as well by dy dx because we differentiate a term with a y. So let's just keep track. We did this one, this one, this one. Now we need -x squared, so that's -2x. Then that's equal to the derivative of -4, and that's 0. Don't forget to differentiate the right-hand side as well. It's easy to forget. So then we want to collect all the dy dx terms, these 3 terms on one side of the equation, and the other terms, put them on a different side. So we're going to bring this 2x over to the other side. So we'll have 3y squared dy dx plus 2y dy dx minus 5 dy dx is equal to, we'll add 2x to 0, and so it'll just be 2x. Okay, so step 2. Then the third thing is to factor out the dy dx from all of the terms that have it on the one side of the equal sign. And then divide by what dy dx is multiplied by. So we'll divide by the 3y squared plus 2y minus 5 on both sides. So here's a formula for the slope of the tangent line at any coordinate x, y that lies on this curve. So any coordinate on this red graph here, we'll just plug it into here and we'll get the slope at that point. So we want to know at 1, -3, that's our first point. So let's go ahead and find that point on the curve, 1, -3, that's down here. So if we sketch in a tangent line at that point, probably looks something like that-ish, maybe a little less steep. Yeah, maybe that's not a great one. So maybe something more like this, probably. So here's the notation that we use to basically tell everyone like, hey, we're gonna plug in a point into dy dx and get a slope out. So instead of, like f prime of 3 for notating that we're plugging in 3 into the derivative, here's how we notate that with the dy dx notation. So we write dy dx, and then we put this bar, and at the bottom of the bar, we put in the point that we're plugging in, so 1 comma -3. And then that's just indicating that after this equal sign, what we're doing is plugging in a 1 for x and a -3 in for y into dy dx. So when we plug in a 1 for x up top, we're going to get a 2, it looks like. Down bottom, we'll get 27 minus 6 minus 5. And I think that that is a 16. And so that comes out to be 1/8. And I'm just going to make this the blue color because this goes with the blue tangent line that we drew. Okay, so the slope here, the slope of this blue line at 1 comma -3 is 1/8. Looks about right. I mean, it's definitely got positive slope. It's pretty, not a very steep line. 1/8 is pretty small slope. So I don't know, it kind of makes sense based on at least our picture. And then we want to find the slope at -2 comma 0. So let's see where that one is. -2 comma 0 is right about here. And the tangent line might look, I don't know, something like this. And we want to find the slope of that. So it should be positive. It should probably be bigger than 1/8. So let's see what we get when we plug in a -2 for x and a 0 for y. So we'll get 2 times -2 up top. Down on the bottom, we'll get 3 times 0 squared plus 2 times 0 minus 5. That puts us at -4 over -5, and that's the same as just 4/5. Okay, so the slope of this pink line here is 4/5. And it's positive and it's larger than 1/8. So at least based on the picture, that is a good indicator of our slope. Or it makes sense at least. All right, 1 comma 1, that is this point right here. If we think about the tangent line to that point, it's kind of the opposite of having a horizontal one, like we would have a peak or like a high point or a low point. So this line, this tangent line here is going to be actually vertical. So we should find that the slope is undefined. So let's see what that looks like when we try to plug in the point. So we have dy dx of 1 comma 1. So we'll plug a 1 in for x up top. And we'll plug a 1 in for y down on the bottom. And that's going to give us 3 plus 2, which is 5, and then minus 5. So that gives us a 0 on the bottom. And of course, that means we have an undefined value. So that makes sense algebraically and graphically, as it should. Okay, part B says find where the curve has a horizontal tangent line. So I'm just going to go over here. So the curve will have a horizontal tangent line, the same kind of situation as we are used to, right? A horizontal line has a slope of 0. So that looks like that's going to occur right here on the graph when x equals 0. But let's see how to do that algebraically if we don't have a picture for it. So, right, this is going to be where the derivative is equal to 0. So we're going to set that whole equation 2x over 3y squared plus 2y minus 5. We're going to set that equal to 0. And the way to solve this, you could think of it in a few different ways. You could look at the 0 as being 0 over 1, and then you can cross multiply across the equal sign. So on the right-hand side, we'll get 0 times 3y squared plus 2y minus 5, and that's just 0. And on the left-hand side, we'll just get 2x times 1, and that's just 2x. You can also think about it as just multiplying both sides by 3y squared plus 2y minus 5, so that cancels down here. But then over on the right-hand side, that's just being multiplied by 0, so you'll still just get 0 out. A third way to think about that is a fraction is 0 only when the top is 0. It doesn't matter what the bottom is, as long as it's not also 0. So solving this for x, we just get x equals 0, and that, again, makes sense based on our picture. And there's no other places, right? Looking at the graph, that was our only spot, so that makes sense. Again, geometrically, graphically, and algebraically. Okay, so I don't know, that kind of shape of this curve here doesn't have a particular name as far as I know. It's kind of like a puzzle piece shape. But this next example that I've got, we're going to look at an asteroid. And you'll see why they are called asteroids, because they look like kind of star-shaped. So let's find the now equation of the tangent line to this curve, x to the 2/3 plus y to the 2/3 equals 2 at the point 1, 1. Okay, so again, this graph here, it has this like nice enclosed shape like this. You can think of it, so it's kind of like a circle. I mean, it's not really like a circle, but this would be to the second power here and here. When you change the powers, the curvature like changes. So we have like less than 1 degree on each of these. And so instead of curving like this, it curves the other way like that. So this is like a nice enclosed shape. There's no asymptotes. It doesn't keep going like this. It literally just has this pointy place, 4 pointy places like that. So this is called an asteroid. So we want to find the tangent line equation at the point 1, 1. So 1, 1 is right here on that purple dot. And if we were to sketch in a tangent line to that point, I don't know, it might look something like this. So we want the formula, the equation of the tangent line. So in the end, our answer is going to look like a line, a linear equation, y equals mx plus b, where the m is, again, given to us as usual by the derivative. So it'll be dy dx evaluated at the point 1, 1. Okay, so m, the slope, is the derivative with the point 1, 1 point we're looking at plugged into the derivative. So I think we have to find dy dx first. So let us say, okay, we're going to differentiate with respect to x. Oops, I miswrote that. Instead of 3/2, we should have 2/3. Both sides with respect to x. Okay, on the left-hand side here, we'll just use the simple power rule a couple times. So we'll get 2/3 x to the negative 1/3. And then we'll add 2/3 y to the negative 1/3. And just that y term where we differentiated stuff with y, that means the times dy dx. Don't forget on the right-hand side, we have to also differentiate the 2, so it becomes a 0 over there on the right-hand side. So I'd suggest that we get, before thinking about getting rid of the negative powers, we'll just try to isolate the dy dx first, and then we can simplify the expression that we get after that. So we've got one term here that's got a dy dx with it. We've got this term here and this term here that doesn't have a dy dx. So I would probably just bring this 2/3 x to the negative 1/3 over to the other side of the equal sign and leave the 2/3 y to the negative 1/3 dy dx on the left-hand side. So we'll bring the 2/3 x to the negative 1/3 over by subtracting it from 0. So on the right-hand side, we'll just get negative 2/3 x to the negative 1/3. All right, then we want to get the dy dx alone, so we'll just divide by 2/3 y to the negative 1/3 on both sides. Now the 2/3 and the 2/3 can just cancel out. We don't need to worry about doing anything like crazy with dividing by a fraction. It's just a number divided by itself. And so no matter what that number is, we can just cancel them out. We'll just get 1. However, the top one is negative, so we will get still have a negative there. So it'll look like x to the negative 1/3 over y to the negative 1/3. That's just like, no need to have all those negatives. We can just move this x to the negative 1/3 down into the denominator, make its exponent positive. And then we can also do things in the bottom if they have a negative power or any power at all. We just bring them up and negate their exponent. So basically, these are just going to switch places, and we can make their powers positive. That's just a little bit better. Okay, so now we want the slope of the lines. We want to use this now to find m, which is going to be dy dx, evaluated at the point 1, 1. So we're going to plug in a 1 for x and a 1 for y. 1 to any power is just 1, and so that'll give us negative 1 for our slope, which makes sense based on our picture. It's definitely negative, and the way I've drawn it with my grid there, it looks like it does have a negative 1 slope. Okay, last but not least, we want to find now basically the b value, or get the equation of the line using our slope now. So I've shown you a way to do this with finding the value of b before. Here's another way. You can use point slope form. So this one's kind of nice because it gives you your equation of the line in a nice form where you don't have to go back and then like put in the b value. So I'll just, if you like the b value and it makes sense to you, then you can by all means just keep using that. But just in case you want another way to think about it, or maybe this one makes more sense to you, I'll show you how to do it this way. So this is called point slope form because you've got a slope and you've got a point. The x1 and y1 are a point that the line goes through. So we leave the just plain y and plain x alone. We know the y value of the point is 1. We know the slope is 1. And we know the x value of the point is 1. And all we have to do is basically solve this for y. So we'll distribute the negative 1 and then add 1 to both sides. And there's the equation of that line, y equals negative x plus 2. Okay, so this line that we drew here, hey, my y-intercept looks good too, right? The y-intercept would be 2, and that's what based on the graph, that's a good, it looked good. There's our equation of the tangent line. Okay, so this is the end of section 2.7. Take some time to look at the web design or try some of the homework on implicit differentiation. So anything where you're trying to find dy dx with an implicit equation. And feel free to come in office hours and work on some problems with me. Otherwise, tune in to see some applications of this stuff to some word problems or some interesting situations where we can use this outside of just in a graphical context.